Hey everyone, so today I just wanted to make a video about doing runtime questions for iterative functions. So here I have written an iterative function. It takes in some integer n, and then it does this double for loop stuff. And so here we're just asking to figure out what is the runtime of this function in terms of n. So there's many variants of this, so maybe you're asked to find the best case and the worst case, or maybe there's a little bit more stuff in this function, but many iterative functions kind of boil down to this representation where you just need to figure out the runtime of kind of a for loop, maybe a while loop. So here I'll show you how to do this one, and then you should be able to generalize it to any new iterative functions you encounter. Okay. So here we have two for loops, which is the usual for loops in 61B. We have these two. You could possibly have more. It shouldn't really make a difference. You would just apply one more layer of what we're about to do. And what I like to do when I see these functions is make a chart of the iteration number. So I'll say iteration number versus the work at that iteration. Work at the iteration. And the reason we do this is because if we just had a single for loop, so if this for loop just happened to not be there, then it would be pretty easy because we just have one for loop. We would just figure out how many times does that for loop run and how much work does it do in each iteration, and we would be done. But now that we have two, it's a little bit harder, especially when the second for loop depends on I. So if we isolate, so we can basically do that first thing I said where you just look at the for loop, how many times it runs versus the work in every iteration, and apply that many different times. So what I mean by that, so let's look, for example, at iteration number 1. So at iteration number 1, let's actually make another column for what does I equal. Okay, at iteration 1, I equals 1. Okay, and how much work is done? Well, we'll start from j equals 0. As long as j is less than I, which in this case is 1, we're going to print something out. So how many times? So I guess what the key thing here is, this print statement is what we're kind of using to determine the runtime. So however many prints there are, that's what our runtime is going to be, or theta of that quantity. Okay, so when I is 1, this thing will only print once, right? And that's because first j is 0, and 0 is less than 1, so it'll go in the for loop, it'll print it, and then it'll update j by 2, because in that second for loop, I say j plus equals 2, and so now j is 2, and 2 is not less than 1, so we'll stop iterating. Okay, so that's that one. Let's do the next row. So at the next row, it's iteration number 2. I is now 2 because we're multiplying. Maybe this is a little unclear, but that is multiplying by 2. And so now I is 2, and now we still get one iteration, and that's because it's j less than I and not j less than or equal to I. So on the second iteration of the for loop, j is equal to 2 and I is equal to 2, but since 2 is not less than 2, we don't go in. Okay, so after you do a few, then you should do where you figure out the, I guess, general runtime. And so now we're going to, we kind of did the first two. We get how it works. We're just figuring out how much this thing runs, right? That number is what goes over here, right? So we kind of know what we're doing now. So now let's say, okay, we're at some random iteration I. So I is some intermediate iteration, and here I use the same variable name as that. And you can, I guess, if you wanted, maybe I could have done k or some different number. That doesn't matter. It's just to kind of show you that, okay, in general, if you're at some iteration I, how much work is done at that iteration. Because that's what we really want to know. If we can know that, then we can figure out our runtime very easily. Okay, so we know that when I equals, some intermediate value I, then we're just going to this intermediate, or the second for loop, the work at the for loop with j, that's just going to run I over 2 amount of times. And how did I get that number? Well, I know that I'm going to go from j equals 0 to j, to basically up to I, maybe I minus 1 or I minus 2, because of the less than sign and not less than or equal to. So about I, it doesn't matter the exact amount. And I'm incrementing by 2. Okay, so for example, if we kind of think of it like this, so j starts off at 0, it wants to get to I, right? This is I over here, and it takes hops of size 2. Okay, so there's one hop, there's another hop, and so on. And so we see that the total number of hops they take, where each of these is like length 2, the total number of hops the total number of hops that it gets to take is just the distance from 0 to I over 2. And that's what I divided by 2 is. Okay, let's get rid of that. Okay, now we have our general formula, and we can actually write out the entire sum. Okay, so this is now this is the part where we figure out this is the part where we deal with the first for loop when I is starting at 1 and I is less than n. Okay, so we just need to sum up this column, the work at iteration. Okay, well, and we're going to use this formula. Okay, so if you want to be mathy, whoops, that's a bad sum. If you want to be mathy about it, we can say the sum where I equals, I guess not quite, because I is getting multiplied by 2 here. So we'll just go like this. Okay, the first term is I over 2, where I equals 1, right? Because that's the first value of I. So 1/2 plus. The second term is, well, what's the new value of I? It's 2 divided by 2. The third term is the new value of I after 2 would be 4, because we're multiplying I by 2 every time. And then, again, we're multiplying, so 8 over 2 plus, and now we have, 16 over 2. And we're going to keep going. And what's the last value of I? The last value of I is n. And we're going to divide that by 2 because of that formula we have here, the I over 2 here. Okay, let's scroll down a little bit. Okay. Okay, so, and this is actually getting added. So now this is the total amount of work that this entire function does. So what we've done is we've split up this in the middle for loop, the j equals 0, j less than I, j plus equals 2. We've split that loop into many different iterations. So let's annotate the sum I have down here. So this is, all of these numbers is the number of iterations, or let's write this. Let's write so this is when I equals 1, I equals 2, I equals 4, I equals 8, and so on. And this quantity, this 1/2, and then this 2/2, 4/2, those numbers are all the work. And same with these. And that would go to every single one. And then we just plug in to our formula here whatever the value of I was. So that's how we got these numbers. And I hope you can see that if we sum that over every single value of I, we'll get the total work that this does, right? Okay, so now let's figure out what this sum is. So first we can simplify a little bit. We know there's a 1/2 in every term. So okay, I'm going to factor the 1/2 out. And now what are we left with? We're left with 1 plus 2 plus 4 plus 8 plus 16 plus all the way up to n, right? Okay, and here's where you should apply the summations that you know. So in case you forgot, we can write them over here. The two super important summations for asymptotic runtime are these. Let me box them. Okay, so 1 plus 2 plus 3 plus ... n. That is I'll use this symbol. It's not equal to, but it's in theta of n squared, where n is just whatever the last term is. Okay, so this is an arithmetic sum. So in this example I wrote, we're adding 1 between successive terms, but you don't need to add 1. You could add some constant number, so 2 or 3 or 4. It doesn't matter, as long as it's not changing. That's the important part. And so no matter what number is like the difference between successive terms, it's still going to be theta of n squared. Okay, and the other important one, the geometric one, is successive terms are multiplied by a constant. In this particular one, it's 2. And this is theta, this sum is theta of n, where again, n is the last term. And so we see that this is a big difference between arithmetic sums and geometric sums. So with arithmetic sums, the whole sum, the value of the whole sum is about quadratic of the last term. But for geometric sums, the value of the entire sum is theta of the last term. So, and that's because in geometric sums, the last term completely dominates the entire sum. So the whole sum is sort of the sum is basically represented by the last term. And that's because geometric sums grow incredibly quickly. And because of that property, we see that the sum is dominated by the last term, as opposed to arithmetic sums. Okay, well now we can apply our summation formula. In this case, it's geometric. So we know that this is 1/2 times, I know this thing is theta of n, and 1/2 times theta of n, again, using what we know about asymptotics, we can completely ignore the coefficients. So we're just going to write that this whole function is theta of n. Okay, so that's how we can do this function. And now I suggest that you kind of play around and see and try to modify this function and see if you can modify it into a different kind of function. Maybe instead of times equals 2 up here, maybe instead of this times equals, you can change that to plus equals. Maybe instead of plus equals 2, you can imagine what if I did plus equals I, or all sorts of weird things. Or actually, plus equals I might be a little difficult. Maybe try like plus equals 10 or some constant and see if that makes any difference at all. So that concludes how to do the iterative asymptotics functions. So to recap, all you need to do is make your table of iteration number versus the work of that iteration, and then sum that. And then that sum will either be one of these two sums that you see here, or it might be easy enough that you don't really need a formula. For example, maybe it's 1 plus 1 plus 1 plus 1 repeated n times. So let me write that out. You might get something that looks like 1 plus 1 plus 1 plus 1, 1, where the number of terms here is n. And then you don't need any formula. You can just know that that equals n, for example. So yeah, that concludes this video. Feel free to play around with the values here and the operations. So I'll see you in the next one.